Good afternoon, everyone. I am Sunandan Adhikary, a research scholar in Indian Institute of Technology, Kharagpur. I am here to present our work, Skip to Secure, Securing Cyber Physical Control Loops with Intentionally Skipped Executions. The work is accepted in CPS and IT Security and Privacy this year as a short paper. Our work is mainly focused on securing the distributed cyber physical system against vulnerabilities like false data injection attack with reduced amount of resources, obviously. Let's start with a brief introduction to false data injection and how what are the security primitives against it to combat them in CPS. Now, the system model that we consider is a typical one, that is a discrete LTI closed loop system with a Kalman filter. Security primitives present in the systems are control theoretic one and a cryptographic one. The control theoretic one is a residue based detector which checks if the system residue is less than predefined threshold. If not, then it raises an alarm saying the system state must have been corrupted. And the cryptographic one is including message authentication codes or message encryptions. It uh, appends a MAC in every sensor actuation data so that it can be verified on the other side. The FDI attacker attacks on the network by polluting the sensor and actuation data. The aim is to obviously make the system state unsafe by fooling any existing intrusion detection system. It is easy to fool residue-based detectors, but for a MAC appended message, it is hard to not raise any suspicion and tamper the message. Now, there are obvious pros and cons to each of the security measures. The detectors impose minimal computation and communication overload, but cannot fully guarantee security. In that case, cryptographic CPS is cryptographic IDS is more useful because it imposes more data integrity, but at a cost of huge resource consumption. But that is why the idea of sporadic IDS comes in picture, because it talks about intermittently running the cryptographic IDS while we put the control theoretic IDS in charge to balance the security and the resource consumption. Now, Yale in Mo and Texera, they have shown how vulnerable can a threshold-based detector be. That is why many global standards suggest cryptographic primitives. Now, the work we take inspiration from is by Ivanov and his associates. They first introduced the term sporadic IDS and calculate uh, a tolerable range of IDS execution relaxation. We try to increase that sporadicity using our formal methodology and verify higher level of security of the system. We first formalize the sporadic IDS model to analyze its performance and its consumption. In case of such CPS, we divide the system state space in three regions to quantify the system behavior under FDI. So the C is the initial region where the system states start from. C1 is the preferable operating region or inner safety region, and C2 is the outer safety region beyond which the unsafe states reside. And when the IDS is inactive, the injected false data will try to take the system outside preferable operating region and to the outer safety region, but we should not let it go beyond the outside C2 because the system state will become unsafe. So before that, we have to turn on the IDS. This time duration is called IDS downtime. And to ascertain safety and performance of the system, the IDS must remain on as long as it takes for the system to bring it back again to C1 while there is no attack present to nullify the effect of attack. And obviously, after every IDS downtime, the IDS will be up again cyclically, and the system comes back again in the normal operating region. So the effect of the attack till now is mitigated by turning on the IDS. So the attacker has to start from the scratch when the IDS is turned off again. Now, as we improve this sporadic IDS using control execution skips, we have to understand what are those. So deadline missing, shared the control platform, and control packet drop in a network CPS is very common. So in that case, the plant, when it does not have the current control update, runs with the last control update. This we mention as the control execution skip. So a tolerable limit can be calculated from the performance margin of system, of which we call a minimum execution rate. Now we use the term control skipping pattern to denote the occurrence of control law executions over time. For a closed loop system, 0 denotes execution skip and 1 denotes an usual control update. Now, control skipping pattern should abide by a minimum execution rate, obviously, to check the degradation due to skipping does not go beyond the performance margin, obviously. Like here, the pattern 11010011 has 5 executions out of 8, which is abiding by the minimum execution rate of uh, 0.5. Now, the pattern will obviously repeat over time. So we leverage the patterns to increase that system resilience. How? So at the sampling period where the control executions are skipped, and the false data injected by the attacker will not go to the uh, plant at all. So it cannot affect the plant state in that iteration. So that is the motivation that we find behind skipping control executions in order to increase attacker's effort, because the attacker will need anyway more duration and more effort to make the system unsafe or to stay stealthy, because the system is running with a control execution skip. So we propose a methodology to formally improve the system resilience of any CPS, which is equipped with control theoretic and cryptographic primitives, by leveraging such control execution skips to reduce the resource consumption. And we show the effectiveness of our algorithm on two intravehicular control loops. So the terminologies that we are using here is minimum attack length, dmin, which is the minimum length for which an attacker has to try to inject false data in a system to stay stealthy and still make the system unsafe. Now, IDS should be must be activated before this duration to ensure system safety, and this actually signifies the system security level. And IDS rate, on the other hand, is another terminology that we use to signify how much. What is the fraction of time the IDS has to be turned on when compared to the system overall system runtime, which denotes the resource consumption of the IDS. To evaluate the security level of a CPS, we design an attack vector synthesis algorithm, which models an attacker using SMT-based methodology and verifies what should be the minimum length for which the attacker has to try in system, so that the system state becomes unsafe and the attacker still remains stealthy. We try this by increasing the number of iterations of attack and trying from all the possible positions of the pattern. Now the intuition is more the duration, more the system is resilient towards such FDI attack. Now obviously we can calculate the IDS downtime because it should be strictly less than the D min. So we can calculate that using this. Now for calculating the IDS uptime, uh, we first initialize the state from outside C1, because while the IDS was off, the attacker must have already taken the system outside C1. So how many maximum iterations will the system need? Our algorithm tries increasing the number of iterations and trying from all the possible positions of the pattern to see when there is no attack, that is when the IDS is up, how long should it stay up. So after having these two values, we can easily calculate the IDS rate. The intuition is less the IDS rate, less the resource consumption by the IDS of the sporadic IDS. So the overall methodology includes takes an input of a set of patterns that are abiding by the minimum execution rate, obviously, for a system, and then verifies their minimum attack length should be more than the periodic execution, and then finds out what are the minimum what are the patterns with minimum IDS rate and outputs them. So the output set of patterns ensure a system will following them will guarantee uncompromised security and performance with reduced resource consumption. To demonstrate the effect of our proposed methodology, we consider two intravehicular control loops like vehicle dynamic control and trajectory tracking controller. The specifications are given here. The safety limit and the sensor and actuation range are taken from a Bosch manual. Now we can see from the plot that the pattern that is output for VDC using our algorithm 1.0, using that, the IDS downtime increases from 2 to 5. Due to that, the IDS rate decreases 30. There is a significant IDS reduction of 37.5%. Now for TTC using 110.10011 pattern, the IDS rate decrement is 27.7%. Now, because during CAN transmission, we need extra 3 packets while we are encrypting the messages, because of increment in sporadicity, this bus load also decreases. That is, decreases by 16.25%. For more control loops with more such sporadic IDS, the reduction will be even further. Now we have some future plans to improve this work. Theoretical explanation how the to the how the skip positions are related to the system security, and how to improve a pattern pruning and SMD solving algorithm, and how can we solve the scheduling issues that arise due to securing physical systems in a shared platform using such sporadic ideas will be a useful extension of this work. Hope the idea is understandable. The questions are welcome. Thank you for your time.